Hi class, this is Dr. Nerz-Stormes. Believe it or not, first time making a movie in a hospital room. I'm okay, as you can see. They're just making me stay here for an inordinate amount of time. So what I decided to do is do this instead of a lecture next week because I think you need a little more time in the lab. What I would recommend next week is to do lab 15, which is the Wittig reaction. That's 15, and to do 17, if you can. Now remember, this is at your own pace, and I still believe you will finish before the makeup week. If worse comes to worse, though, you can finish a couple things up in the makeup week, but I think that's unlikely. And I would do experiment 17, which is the aldol reaction. These procedures are on the website, on the web book. You just have to click on them and download the procedures. The aldol has two procedures. One procedure is a smaller scale microwave procedure that involves about 0.1 grams of material. And the reaction's done in a microwave. Do not do that reaction. It gives it works, but it doesn't give great yields on all the reactions. There's a really good procedure in there. It's later in the it's a little bit later in the experiment 17 pages, okay? And it involves taking about 0.8 grams of material, putting it in ethanol, all right, and kind of refluxing it in a giant test tube. Do that reaction. Okay, that's what I would do. This reaction should take you about 2 hours. This reaction will take about, you could do it in 15 minutes, but it'll take about 30 minutes to totally complete it. It's very, very easy, and you could kind of run both of them at the same time since you have a team. The other thing is, if you want, you could TLC your experiment 26. Now remember, there's not going to be any write-up for this, but I still want you to go through the process of doing the TLC, doing all the stains, okay? So you can take your product, spot it again. This week my recommendation would be the opposite of last week, of 2 weeks ago. It would be to put more material on the plate, because some of you with your sample, you diluted your sample down, you over diluted it, and you were getting very light spots. So try to get darker spots so you can see that warfarin. And you want to just put it under the UV light. You don't really have to use the iodine chamber unless you want to. And then use the stain, okay, the anisaldehyde stain, okay. And again, I'll probably be there on Monday, and I'll be there in lab, but I'm probably not going to hold a lab lecture, okay. Maybe something short, but I probably won't. Okay, so do the TLC experiments if you can, but I would say definitely get those two. Try to do that if you have time. Don't kill yourself, but if you get these two, you'll be well on the way of your synthetic project. Okay, so let's start. And then if you want, you can isolate the product with this. A few people have done it. Some of the reactions have worked very well. Now remember, with the anisaldehyde, the para-anisaldehyde stain, one of the starting materials stains white, one stains red, and the product stains blue, and it's really a really beautiful blue. I can actually send you my picture of that because I have a couple pictures of it. Okay, now I need an eraser. Hold on a sec. Okay, so let's start with the Wittig reaction. So I'm going to start with the theory behind it. Okay, what you're trying to do is make this compound. Okay, this is called Nerz-Stormes. Nerz-Stormes is a solid, okay, and the byproduct of the byproduct in most syntheses is Stlbene, which is a liquid. So fortunately, in a Wittig synthesis, you get this. Stlbene is a liquid. So because it's a liquid and this is a solid, as you might guess, they're easily separated. Okay, now to make an alkene, there's a lot of ways you can make an alkene. There's a lot of routes, and if you looked on the internet, you probably found different ways to make it. But one of the easiest way to make an alkene is a Wittig. So I would add onto your list of carbon-carbon bond forming reactions that a double bond construction suggests the use of a Wittig reaction. And we're actually going to connect this piece to this piece using anion chemistry again. So you'll see our theme this semester is very much about how carbanions attack carbonyls, and it's going to involve a carbonyl as well. So the way you do this, so actually what I'll do is I'll look at it retrosynthetically. So if I were thinking about this backwards, okay, or retrosynthetically, what I would think is if I'm going to use a Wittig approach, my precursors to this would be this compound, or this anion, this anion is called, and now these little phi's that I'm drawing here, these Greek letters that I'm drawing here, are representative of benzene rings. So this equals benzene. Okay, that equals benzene. I'm going to erase that because I think that's going to be confusing. But each one of these is a benzene ring, and it's just a way for me to consolidate a little bit because it's so there's so many benzene rings in these structures. I would react this with benzaldehyde. Mark, can you see those?
Yeah, pretty clear.
Because of the black, you can see it. Mm-hmm. So you would react these two together. Now, when I write the mechanism for this, what's going to happen is this anion, as you would guess, is going to hit the delta plus carbon. And that's become a theme in all our reactions. Now, where does this come from? This comes directly from, notice I'm going backwards. This is really hard for people sometimes to see someone do a retrosynthesis. This comes from a phosphonium salt. And we're going to specifically use the chloride, but you could also use the bromide. The bromide's actually a little better, but it's much more expensive. This is what's called an elide. Okay? It's called a phosphonium elide. Okay, and ilids, or elides, are compounds that have a positive and a negative charge. And there's actually another resonance form you can draw of this with the negative charge in. Now, where would I get this from? This you guys are going to get right out of a bottle. But if I wanted to make this, you'll get that right out of the bottle. If I wanted to make it, I'd make it from, it's kind of interesting. I would make it from the chloride, the benzyl chloride, and I would just add, I don't know why I feel like I'm writing backwards. I would make it from this. And it's kind of an interesting thing. That looks like the Philly symbol there. It's kind of interesting because all this is an SN2 reaction. And remember what when we spoke about the periodic trends, and we said the larger atoms are really good nucleophiles. They're excellent nucleophiles. So a phosphorus with a lone pair on it is a better nucleophile than a nitrogen with a lone pair. So this is actually a pretty good nucleophile. And you might think about this, you're like, oh my goodness, there's all these groups on it, it's very sterically hindered. But when you get a big atom, there's much more distance between the groups, so this doesn't really have steric hindrance. Think about it, if you have a giant ball with these groups hooked on it, and this is a giant ball, they're not really going to be that close to that lone pair. So the lone pair is going to come in, hit that, knock that out, and that's how you get that phosphonium salt. And what kind of reaction is that? That's just an SN2. Okay, so let's look at the mechanism for this. Okay, so if I want to make that, I would really start with these two. Make benzyl phosphonium chloride. It's triphenyl. It's benzyl triphenyl phosphonium chloride. Then I would have to take a proton off that. Notice I'm removing a proton to make a carbanion, and then it's very much like a Grignard reaction. It's just going to attack the carbonyl, but it's a little different because that phosphorus has a positive charge, and it's capable of becoming hypervalent. And that's going to ultimately form this double bond. And so we'll make trans-stilbene along with some cis-stilbene. Okay, so let's write the mechanism. What's my time right now?
9:45.
Okay, so going forward, now I'm going forward. So I'm going to take this benzyl you guys, again, you're going to get right out of the jar this compound. You should be very careful with this compound because it is pretty toxic. It is a solid, but you have to transfer it, very carefully with a spatula. Don't cross-contaminate things, okay? Now, normally, if you're reading in your textbook, and you read about this in your textbook, you'll see they use very strong base. So normally, they'll use a base like super base to pull this proton off, all right? But we're going to do this a little differently because this is pretty acidic, and you can think about why it's acidic. When I pull the charge off, I'm going to have a lot of resonance stabilization. So what we're going to use is 10 molar NaOH, just good old NaOH. That you'll be using hydroxide all day if you do both these reactions. And we're going to do the reaction in dichloromethane. Now I'm going to talk about that a little later because this immediately implies that we have a two-phase system because the 10 molar NaOH is in water and the dichloromethane is not in water. Okay? So what's going to happen here? Well, what we hope will happen is this will pull this proton off. This comes off and you get a resonance stabilized anion. And you guys can write out all the resonance forms. It's good practice for you. And again, why am I getting away with this? I'm getting away with this because there's resonance stabilization. Now, where is that resonance stabilization? It's over here, it's through here, and around the ring. So there's resonance stabilization of that charge. Now, I'm showing you where it's really going to attack. Okay, so I'm just going to draw that without the resonance stabilization. Okay, so now I've got my anion, and I have my good old carbonyl here. I'm trying to write a little neater than I normally do. Let's hope it's a little neater. And this anion is going to come in and hit this carbon and open up that bond, that pi bond, and the charge is going to go on oxygen. Okay, and what will that result in? That's going to result in a carbon-carbon bond, which is, of course, is always an exciting event in chemistry to make a carbon-carbon bond. But what's really exciting about this is that we will ultimately get from this a double bond. So we're going to make two carbon-carbon bonds. All right. What am I missing here? Something is missing. Oh, the phosphorus. Okay, we're going to get this. Okay, now this is called a betaine intermediate. And, this reaction, there's, I've read a lot about it. There's a lot of, controversy about the mechanism. I still read things about people studying the mechanism. So it's not, very well defined whether or not we get this at all. But this will ultimately jump into the phosphorus and form a bond. And think about it, what kind of ring am I making there? I'm making a four-membered ring. Okay, so let me draw that. So again, this may or may not be the first intermediate, and I'm missing a hydrogen right there. Okay, now when this forms, okay, what's it going to look like? It's going to look like this. There's going to be a phenyl. And I'll put little wiggly lines here. And there's going to be another phenyl over here. The wiggly lines mean I'm just not specifying stereochemistry. And you know how wild I am about stereochemistry. And this reaction should form at this juncture what's called an oxaphosphatine. And again, you can read about this in your book. Now, reactions that involve aromatics frequently form trans products. So that would imply that we're going through something like this to form the trans product. Now again, this reaction is controversial, and the mechanism, I think, is much more complicated than this, just based on things I've read recently. It's just not a simple reaction. Because some things form mainly cis, some form mainly trans. If you change the conditions, sometimes you'll get more cis than trans. But this particular reaction gets more trans than cis. One thing you could think about is just when they're coming together, you might say, well, it might be best for the phenols to be on opposite sides. It's just something to think about in terms of stability. But this ring itself, and notice what's happening here. The phosphorus is taking an extra bond, and bigger atoms can do that. Think about sulfur, right? So it's taking this extra bond in, or phosphate. If you've studied biochemistry, you'll see phosphorus with 5 bonds. This is a normal state for phosphorus, but this little ring is not stable, and you guys can think about what's not stable about it. It's 4-membered ring, so it has ring strain, and what happens is it collapses, and it collapses like the opposite way, so that there's a double bond here and a double bond here. So there we're making our trans-Stlbene, and so we get trans-Stlbene. Make sure you work through this. I want you to work through it and think about it. Read about it in your textbook. That's just awful looking. You'll get this. That's trans-Stlbene. And the byproduct, which is kind of interesting, is called triphenyl. And again, I'm abbreviating these. These are benzenes, just like these. Okay? This is called, again, trans-Stlbene. This is called triphenyl phosphine oxide. Okay? And it's kind of interesting because it's one of the only reactions you've done where you get an organic byproduct that is undesired, and you're getting it in this exactly the same ratio. So for as much trans, and you'll also get the cis. You're not going to just get the trans. So you'll have the cis and the trans. So we got to get rid of this, and we've got to get rid of that. Okay? So it's problematic to get rid of organic side products because their properties are more similar. Inorganic byproducts are easy to get rid of, as you've discovered through the year, because most of the time you've had inorganic byproducts. So this thing's a little bit of a bear to get rid of. So now I want to talk about the experiment itself a little bit, pretty briefly. Your setup is basically just, this is probably going to be an awful picture. It's basically just, it's kind of like what you did last week, or 2 weeks ago. I'm losing track of time. Okay, what is that? It's sort of a bad looking condenser. Remember to put a clamp here. We're really having a problem with that. I've been trying to, oh my gosh, that doesn't look like a flask at all. I'm not in my dining room, so I don't have my good angle. Okay, so let's say this is your reaction. I would recommend doing it on 2 to 3 times the scale written in the lab book. You're going to need a lot of this stuff. You don't get a good yield on the reaction. And you're going to need a lot of it. So this will be water in. This is water out. And so what you're going to put in the reaction, you're going to put 10 molar NaOH. You're going to put dichloromethane. Immediately you're going to have two layers. So the top layer is going to be the 10 molar NaOH. The bottom layer is going to be CH2Cl2 for the most part. Then you have to think about where are things going to go when you put them in there. So the bottom layer is definitely going to have the benzaldehyde, because benzaldehyde is really nice and soluble in the organic solvent, as you might expect, because it has 7 carbons and only 1 polar functional group. So that's going to be down there. And so think about this. We got a problem. We got a problem because our base is up here and this is down here. Now the interesting thing about the benzyl triphenyl phosphonium chloride is that it is really polar in a way, right? Because it's got an ionic interaction. So your gut instinct would be, oh, this is going to go in the aqueous layer. And that's a big problem because one reagent's up here, one reagent's down there. But this also has 4 benzene rings. That means it has 20 carbons, or actually, sorry, 21 carbons. That makes it somewhat hydrophobic. So this actually has what I would call dual citizenship, in that it's going to migrate between the 2 layers. It's what we call a phase, in a way. It's not a classic phase transfer catalyst, but what it's called is a phase transfer or it could be classified as a phase transfer catalyst. At least people call it that. Now again, you can read about this in your lab book. So but we still have a problem. Even though this has dual citizenship and it can travel back and forth, we really have to stir this like crazy. So one of your problems is that you're going to be heating and stirring this. So you have to stir through a heating mantle. And you're going to have to keep this stirring. It's extremely important because what you want to do is get those layers to really interact with each other, so the molecules are going to move faster between the layers, right? It's like an extraction. If you really get them interacting, there'll be a greater surface area between the layer, and this will move faster between the layers, and you'll get a much faster reaction. Okay, so what's going to happen? What you want to have happen is you want this to travel back and forth. Okay, so let's write that. So you want this in the aqueous layer. What time is it?
21.
All right, I'm going to stop this one in a minute. So in the aqueous layer, you want this phase transfer catalyst. And some of it will be in the other layer, but eventually it'll travel up to the aqueous layer. Now, what's in the aqueous layer? The aqueous layer this is a chloride. It has hydroxide in there. And what you want is for this to trade its partner. In other words, to trade the chloride for the hydroxide. So it becomes the hydroxide. Somewhere along the way, the hydroxide has to pull this off. Okay? And you'll get this, okay? And it has to travel at some point. It could happen in either layer. My feeling about this is it trades partners, and then it goes into the organic layer. So, it trades partners first. It goes into the organic layer, so it's sitting, I'll put a more phase transfer type mechanism here. Goes into the organic layer. Then it loses this proton. Okay, but it could happen earlier, but it probably travels with that. So think of it as trading partners up here. Coming back with the hydroxide that it needs, becoming the anion that it needs to become. And then, at this point, it's down in the organic layer. It can react with the benzaldehyde, like that, doing the mechanism that we described. So what I want you to be very mindful of is you really have a problem there. One of the reasons you get very low yields in this reaction is because it's two-phase. And you can't just let them sit in reflux. It's got to reflux with a lot of mobility and a lot of interaction between layers to get this to do this. Okay? If it goes too slow, you're going to get a really bad yield. So make sure it's stirring, and it has to be stirring really vigorously. And if it's working, it usually gives kind of a yellow color. Okay, so that's all I'll say about that one for now. I'm going to make another little video about the aldol.